Good evening, everybody. My name is Nirjhar, and today I'll be presenting our paper titled When Oblivious is Not, Attacks Against OPAM. We'll start off with the presentation roadmap. We'll first have an introduction to enclaves and what ORAMs or Oblivious RAMs are. We'll then describe how InvisiPage or OPAM works, followed by the attacks and the vulnerabilities that we have found out and applied on them. We'll discuss a covert channel that is possible using reduced distances. So reduced distance is a term which we coined. We'll demonstrate how it works, and then we'll be ready with the conclusion. So what are enclaves? So enclaves are just a hardware-provided isolated environment where applications can execute in a much secured way, such that even if high-level or higher privileged code, like the operating system code or the device driver code, is malicious, it won't be able to leak secrets from that. So ORAMs. ORAM stands for Oblivious RAM. So what it does is, let's see with this diagram. So there is a client which is trying to access a data at location I, so which is DI. So it sends the index or the location to this ORAM interface. ORAM interface interacts with an untrusted server in the following way. So if it tries to access location I, what ORAM interface will do is it will access location I, followed by it will access many other locations. And then it will return the desired content or data at location I. So what happens is, since this ORAM interface accesses multiple locations, the untrusted server gets confused and is unable to figure out the access pattern of the client. So so ORAM is just an interface. So also the data is shuffled. So after I is accessed, the entire memory is reshuffled, so that next time when I is again this location I is accessed, it will be in a separate location. So it hides access patterns, and some examples of ORAMs are some tree-based ORAMs like path ORAM, ring ORAM, and square root ORAM, which is not a tree-based ORAM. So how does ORAM fits into the demand paging inside enclaves? So there is this enclave application which is running in a sealed environment, and a page fault occurs. So it is sent to this runtime. So runtime is just a mini OS or a mini kernel for the enclave app, which is also a part of the trusted component and runs inside the enclave or sealed environment. So this runtime is basically responsible for handling various types of page faults and other interrupts, so that the control doesn't go to the untrusted host operating system. So so this the page fault goes to this runtime, and the runtime basically sends the page faulting address to this ORAM interface. The ORAM interface sends out a bunch of addresses or indices to this host OS. The host OS interacts with the untrusted memory, fetches the page contents, which are of course encrypted and as well as authenticated. The OS sends it back to the ORAM interface. ORAM interface sends the required page in the runtime. The runtime decrypts it and authenticates it, and the control comes back to the enclave app and execution resumes. So here the threat model is like the host OS tries to find out the access pattern of this enclave application that is running. But what the host OS ultimately observes is that a set of pages gets read in, and then or a set of pages get evicted. The attacker or the host OS can try to modify the pages, but it will be detected in the runtime because all the pages are authenticated. Even if the attacker has some access to this physical access to the untrusted memory, it won't help because of the fact that the contents are encrypted. And we do not consider any kind of microarchitectural type of attacks. We are only concerned with software attacks. So our contributions: first, we discovered a vulnerability in InvisiPage and then systematically exploited it to form an attack, which we call as the reduced distance attack. We of course implemented demand paging inside Keystone. By the way, the current version of Keystone do support InvisiPage. They have their own system, but we have a separate system of our own. Then we exploited this vulnerability to form new attacks. The first one is called the reduced distance attacks, and the second one is called the level tracking attack. We also designed a covert channel, which is designed or which is formed using this reduced distances. We'll see what reduced distances are. So first we'll describe how InvisiPage or OPAM works. So in InvisiPage, the metadata tree is decoupled from the data tree. So the metadata tree contains some description of contains the metadata of the pages, and the data tree contains actual pages or blocks. So this red color indicates that they're in the untrusted world, while the green color indicates that it is in the trusted or sealed memory region. So these red locations are completely accessible to the operating system. Although we show the page numbers as 100, 692, something like this, but they are actually encrypted. So the OS, the untrusted OS won't know that this is the content is 100. So it will see some gibberish, some encrypted content. So we have kept it for the sake of simplicity. So let's say the client of the Enclave application tries to access page number 88 and it's a fetch. So what happens is it reads from the position map, it tries to read the path, the metadata tree path, to find out where exactly in this path the target page resides. So the contents, so the metadata contents are fetched into the Enclave. They are of course decrypted and authenticated, and then a check is performed as to where in this path the tree lies. I mean the page lies. So the page lies here. So this page is, so now the actual page is brought in and it is decrypted and authenticated. And then of course this page is now remapped to a different location. The 0 is just a random number. So this remapping is done using a random number generator. Now, the next phase is the shuffling phase. So the first phase was the page read or ORAM read stage, and this is the path write or path shuffling phase. So here it works in the following way. So first we write we try to construct the path. So here we see that the path 2. So in the previous slide we've seen that we read path 2. So we'll try to reconstruct or rewrite this same path. So in path 2, 250 is the only node that can be placed because it is mapped to leaf 2. So so 250 comes here. Then we're able to, then at this location we can place a page which is either mapped to 2 or 3. So we place 100 because 100 is mapped to 2. So it comes here, and no page can be placed at this point because there is no more page available to be placed here. So yeah. So what happens? So what happened is that if we see the last two figures, here the arrangement was 100, 250, and 88, and after shuffling, the pages look like 100 and 250, and 88 was read, so it is no more present in the tree. So this shuffling is totally done outside the Enclave, and the OS can easily see how the shuffling is done. So the Enclave application basically sends the commands to shuffle, but the shuffling is done outside the Enclave, and the contents are not re-encrypted. That is the shuffled pages. So 250 is not re-encrypted, 100 is not re-encrypted. This is a vulnerability, as we see in the next slide. So on every page fault, we see that exactly one page gets transferred, and the adversary is able to observe which page got exchanged. Since only one page gets exchanged, that means it is definitely not a dummy page, and the host OS or the adversary can find out number of intervening ORAM accesses or faults between two successive page faults. So if there is a page fault P, another page fault Q, the adversary is able to calculate number of intervening page faults. This makes OPAM not oblivious, and this is a vulnerability. So what is the reuse distance? So reuse distance is if a page P gets evicted at a time t0, and then it is again fetched or reused or brought back to the Enclave. The reuse distance is number of intervening page faults or ORAM accesses in between those two times t0 and t1. If we are able to get such set of or sequence of reuse distances, it will be different for different applications. We found this by doing experiments, and we are using this unique sequence of reduced distances, we can distinguish or predict which application is running inside the enclave. So this is a concrete example. So this is application 1, which is trying to access an array continuously in a linear fashion, whereas this accesses a binary tree, which is in the form of an array. So we'll assume that the enclave has 2 physical pages with LRU being used. And so we see that for every page, so for every iteration, the reduced distance for every page here is 2. So when page 2 is accessed, the enclave has pages 0 and 1. So page 0 gets evicted. When page 3 is accessed, 1 gets evicted. So next time when again 0 is accessed, we see that number of faults between the time 0 was evicted and gets refetched, it is 2. So 2 faults means that page 2 was evicted and page 3 was evicted. So number of faults is 2. So for every page, the faults is 2. Similarly, we in this case, number of faults is for every page is a multiple of 2. So the root node will always be 2 because it is accessed in every iteration. The other internal nodes might not be accessed in every iteration, but by working it out, we can see that every internal node will be reused after even number of faults. So the reuse distance for every page is a multiple of 2. So the attack, we'll now describe our attack methodology. So we have seen this similar diagram in a previous slide. So this enclave application, it tries to it causes a page fault, control goes to the runtime, the runtime calls the ORAM interface. In this case, it is the InvisiPage or OPAM interface. And let's say it is calling, making an O call to evict page 88. So the OS records page number 88. Again, this 88 is just an encrypted address. So it's something you need. It need not be 88. So, and yeah, so the control comes back to the InvisiPage interface, and the application resumes. So in this way, a couple of page faults occur, and after some time again, and these page faults are recorded. Then again, the enclave application tries to fetch page number 88, which it evicted some time back. So the same drill goes on, and a call is made for 88 to fetch. So again, the OS records this access. So 88 read, and the control comes back. So we can see that between the time between 88 was evicted and 88 was read or refetched, the OS is able to record the number of faults in between, and this is basically the reuse distance. So if you can get such reuse distances for all the pages, it will be different for different application or different memory access patterns, and hence InvisiPage is not memory access oblivious. So what we did was we collected a trace of reuse distances for many apps, and every application was executed for a couple of inputs. And then we trained the sequences using a convolutional neural network sequence classifier, which takes in a sequence and classifies it into one of the n classes. So here n is just the applications. And for testing, we took a random reuse distance trace for an application which the CNN has not seen. I mean, we take a sequence of an application, and the sequence was not seen or trained in the CNN sequence classifier. And then we try to measure how is it able to detect or classify unknown sequences. But yeah, the sequence has to be of a known application. The sequence might be different, but the application has to be, of course, known, because number of classes is fixed in a training. So this is the accuracy that we have got. So we executed on 100 to 200 inputs for these 8 applications. So we divided the entire data set into 3:1 ratio, and we repeated it multiple times so that we get an accurate value, and there is no overfit or an underfit issue. So yeah, so, and the splitting was also done randomly into training and test data sets. I will now describe covert channel using these distances. So the model here is that so there is this Enclave application. There is this Enclave application and a host operating system. So they're not allowed to pass any message. So they're not allowed to pass any message. If it tries to pass a message, it will be blocked. But what they can do is it, of course, do some page exchanges during paging. And the host OS can observe the trace of page faults. And the Enclave application will try to engineer or try to cause a sequence of page faults and hence a sequence of reuse distances in such a way that the host OS is able to process them and infer the message that the Enclave application is trying to send. So in this case, the Enclave app as well as the host OS, they're colluding with each other. So this basically the page fault or this page fault is basically the covert channel, which is used by the Enclave app to send messages. So it's a standard Enclave threat model where only the Enclave application is trusted, and we consider only software attackers. As we have said, we do not consider any microarchitectural side channels. The Enclave application and the host OS colludes with each other, and the host OS is aware of the encoding which is used by the Enclave application to transfer the messages. So we'll take a concrete example over here. So we'll assume that the message that the Enclave app wants to send is 1001. So the length of the message is 4 and the arity is 2. So 1001 in binary is just 1001. So, and page replacement policy is FIFO, and the Enclave has 4 physical pages. Now to transmit bit 1, we will try to generate a reuse distance of the range 8 to 16, which corresponds to bit 1 and 8. And for bit 0, it is 9 to 16. Okay, so yeah. So first, A stands for access and E stands for evict. So so the application first accesses first 16 pages and the adversary observes the first 12 pages getting evicted, followed by the access of page number 1, because we're trying to the Enclave application tries to send a bit 1. So it must access page between 1 to 8, followed by 0. So it should access a page between 9 to 16. And then again 10. And then this is 14. So we got the sequence of reuse distances as 12, 5, 5, 14, which corresponds to bits 1001. And hence the Enclave is successful in sending the message to the host OS via page faults. So we have done an analysis of the bandwidth. So peak with an arity 4, we see the maximum bandwidth. And as we decrease the arity, as we increase the arity, the transmission bandwidth decreases. So at 4, the bandwidth is maximum because in each page fault, as we have seen in the previous slide, each page fault in this case corresponded to 1 bit. But if the arity is 4, then every digit will be either 0, 1, 2, or 3, which corresponds to 2 bits. So every fault would have contributed 2 bits, and hence the bandwidth increases. But on further increasing the arity, the initial number of page faults, which was 16 in this case, increases, and this overhead basically brings down the overall bandwidth because of the high performance overheads of page faults. Because every page fault involves page transfers, encryption, decryption, authentication, these things. A context which is between Enclave and the outside non-Enclave world. So we conclude now. We have introduced a new side channel attack, the reuse distance attack, which is able to infer confidential information about Enclave's execution, followed by a new covert channel where even if the Enclave application is not allowed to send information on messages explicitly, it can do it using page faults, which is a covert channel. We exploited found and exploited systematically a vulnerability in one of the state-of-the-art approaches to secret demand paging, which is InvisiPage or OPAM. Yeah. So this paper is dedicated to our advisor, in memory of our advisor, Dr. Pramod Subramanyan. We're very sorry that he is not amongst us anymore. Thank you. This work was supported by ACRB India, and I'd like to thank all the authors, all my co-authors, Nikhil Bansal, Nikhil Mittal, Gourav Takhar, and our advisor, late Dr. Pramod Subramanyan. We will take questions now.